Okay, so in this video, we are going to start with D and F block elements. This is the very first video for D and F block elements. Okay, and thus firstly, we will discuss about D block elements and then we will move on to the F block elements. So starting with D block elements, we will discuss its number of properties. Okay, its different properties of D block elements that we are going to discuss. So the very first is general electronic configuration. General electronic configuration of D block elements is n-1 D 1 to 10 ns 1 to 2. Okay, but in case of zinc is having atomic number 30, but it is not considered as a transition metal. Why? Because in this, all the d orbital that is completely filled and s orbital is also completely filled. The configuration of zinc is argon forest 2 3d10. Okay, so that's why it is not considered as a transition metal, because it is having completely filled d orbital and s orbital. But d orbital d block elements mainly refers to those which are having unfilled d orbital, like 1 2 like 9 number of electrons they are lying in that. But still, it's in controversy that if it has to be considered in transition metals or not. Okay, discussing about the physical properties of these d block elements. Physical properties: C, except zinc, cadmium and mercury, all d block elements, they are hard and they have high melting and boiling points. Okay, except zinc, cadmium and mercury, all d block elements, they are hard in nature and they have high melting and boiling points. Okay, now why they are hard and they have high melting and boiling points? Then reason for that also is that they are having more number of electrons in n-1 d orbital. Okay, n-1 d orbitals, they are unfilled, that's why they are hard. Then we have to discuss about the atomic size. See, size decreases due to increase in atomic number. As atomic number is increasing, so size is decreasing. Why is it so? See, d block elements, they have poor shielding effect. Their shielding effect is quite poor. So as the atomic number is increasing, the size is decreasing. Okay, now what is poor shielding effect? Shielding effect means that, for example, this is the nucleus, okay, and this is the d subshell. Okay, and this d subshell is not able to shield these electrons in the 4s. Okay, and this is 3d and suppose this is 4s. Okay, so this nucleus, it has a high nuclear charge, and as d orbitals, they are not able to shield the 4s electrons. Okay, not shielding means that this nucleus, it will attract the electrons of 4s towards itself. Okay, because it is not able to protect them. Shield means to protect these 4s electrons from the force, nuclear charge of the nucleus. So as that is not happening, because they are having poor shielding effect, and so size is decreasing. Okay, now there is a very important and different property that is seen, that is lanthanoid contraction. See, what is lanthanoid contraction? Lanthanoid contraction means that second and third d series, okay, second and third d series, they have almost same size. Okay, they are having almost same size. Why is it so? It is because these 4f orbitals, they are filled before 5d. Okay, 4f orbitals, they are filled before 5d, and so poor shielding effect is there. because of this poor shielding effect, okay, this lanthanoid contraction happens, and second and third d series, they have almost same size. Okay, for f orbitals, they are filled before 5d. Okay, this is very important. Then there is ionization enthalpy. See, in ionization enthalpy, there is no fixed order that is seen. Okay, now ionization enthalpy simply has one rule, that as size will be large, so ionization enthalpy will be less, because nucleus and valence electrons, they will be quite away from each other, and lesser nuclear charge will be there. And in the atoms, or in the elements which are having smaller size, nucleus and valence electrons, they are in proximity, very close to each other, high nuclear charge, so ionization enthalpy is high. Okay, so that is the scene. There is not any fixed trend which is seen in the ionization enthalpy. Then in this, we are having oxidation states. Okay, now different elements, they show different types of oxidation states. Now, for example, manganese, it shows +2 to +7, all these oxidation states. From +2 to +7, all oxidation states are shown by the manganese. In titanium, +4 oxidation state, that is more stable. Okay, and zinc shows only +2 oxidation state, because its d orbit t subshell, that is completely filled. Okay,